Imagine, just for a second, that you're designing a submarine. Obviously, you'd need to know the exact properties of the water you're diving into, right? The pressure, the density, the temperature. But what happens when you're designing an aircraft, or maybe a rocket returning from space? The water you're diving into is the Earth's atmosphere, and to understand how to navigate that, we need to completely reconstruct the very air we fly through from absolute first principles.
The 19th century writer John Ruskin actually described the sky perfectly. He called it never the same for two moments together. And you know what? Scientifically, he hit the nail on the head. The Earth's atmosphere is a remarkably chaotic dynamic system. It is literally always fluxing. The pressure, the temperature, the air density outside your window right this very second, it depends on your altitude, your latitude, the time of day, the season. I mean, even solar sunspot activity millions of miles away can actually change the density of the upper atmosphere.
Which brings us to a massive engineering paradox. How on earth do you design a plane when the sky is literally never the same twice? Think about it. If Boeing is designing an aircraft in Seattle and Airbus is designing one in Toulouse, how do they reliably compare their performance? So the absolutely crucial point here is that to test and build flight vehicles on a perfectly even playing field, engineers had to invent a standardized mathematical fiction. We essentially had to build a fake sky.
So how do we systematically construct this mathematical sky? Well, here is our roadmap for this explainer. 1. The chaotic sky problem. 2. Balancing a block of air. 3. The gravity complication. 4. Geopotential altitude explained. 5. Building the mathematical atmosphere. And 6. The model's limits.
Let's start with part 1, the chaotic sky problem.
To really grasp why we need a single unified testing environment for aerospace engineers everywhere, we have to clarify our ultimate goal. When we talk about creating the standard atmosphere, we are not trying to predict tomorrow's weather. This is not meteorology. Instead, we're building a reliable, unchanging baseline map of pressure, density, and temperature. We need a common set of reference conditions so that an engineer testing a wing in a wind tunnel today can perfectly match up their data with a flight test conducted 30 years ago. It's essentially the universal language of aerospace performance.
Moving on to part 2, balancing a block of air.
But how do we actually calculate the exact numbers for this universal language? Well, to build our sky, we have to start with a fundamental physics rule called the Hydrostatic Equation and a single hovering chunk of air. Just picture a microscopic, rectangular block of air hovering completely still in the air right in front of you. Because that block isn't moving, it's not falling to the floor or shooting up into the clouds, all the forces acting on it have to be perfectly balanced. On the bottom of this block, the air pressure from below is pushing up, but on the top of the block, there's a slightly lower pressure pushing down, plus the actual physical weight of the air block itself pulling downward toward the Earth. For this tiny block to just hover there, the upward pressure from below absolutely must perfectly balance the downward pressure and the block's own weight.
When you translate that hovering block into math, you get this beautiful foundational formula, the Hydrostatic Equation. Let's break this down term by term because it tells a really intuitive physical story. dP is the incredibly tiny change in pressure between the bottom and the top of our block. Rho is the density of the air, g is the acceleration of gravity, and dHg is the tiny physical slice of geometric height of our block. Now, you might be wondering, why is there a negative sign in there? That is actually the most important part. It simply means that as your height increases, as you go up, the pressure must drop. Here's a great mental rule for this. Think of the atmosphere like a giant dog pile. The guy at the absolute bottom feels the weight of everyone on top of him. But as you climb higher up the pile, there are fewer people above you, so you naturally feel less weight. And less weight means less pressure.
Which leads us to part 3, the gravity complication.
Now, what's really fascinating and frankly kind of a nightmare for the math is a complication hiding inside our neat little equation. Gravity isn't actually constant. Isaac Newton taught us that gravity varies inversely with the square of the distance from the center of the Earth. If you drop a tape measure straight down from a plane to the ground, that is your geometric altitude, the actual physical distance to sea level. But gravity is measured all the way from the center of the Earth, which we call absolute altitude. This means as you fly higher, you get physically farther from the Earth's center and the downward pull of gravity physically weakens. Because gravity, that g in our equation, is constantly changing as you climb, our simple hydrostatic equation suddenly turns into a massive calculus headache. You can't just easily multiply the terms anymore. You actually have to integrate a constantly changing variable over distance.
All right, part 4, Geopotential altitude explained.
Now, aerospace engineers, as a general rule, absolutely hate unnecessary calculus. They want clean, solvable equations. So, to build the standard atmosphere, they invented a wildly clever workaround to completely bypass this gravity problem. And this brings us to a massive conceptual leap: the difference between geometric and geopotential altitude. Geometric altitude is reality. It is the actual physical tape measure distance. Geopotential altitude, on the other hand, it's a mathematical fiction. It is a completely fake altitude we invent by pretending that gravity never ever changes from its standard sea level value, no matter how high up you fly. Geopotential altitude is essentially a fictitious map we draw just to make the math easier, while geometric altitude is the actual messy physical territory.
So here is how the trick works in 3 steps. First, we literally freeze gravity. We declare it as a constant 9.8 meters per second squared, forever, end of story. Second, to keep our physics equations perfectly balanced and truthful, if we artificially inflate gravity at high altitudes, we have to artificially shrink the altitude to compensate. So we swap the real geometric height for our slightly altered, fictitious geopotential height. Third, with gravity now locked in as a constant, we can pull it completely outside of our calculus integrals and solve the equations easily. By pretending gravity never changes, we trade a complex physical variable for a slightly tweaked height measurement, totally unlocking our ability to calculate the whole atmosphere.
Now, you might be thinking, hold on, isn't it wildly dangerous to just invent fake altitudes to design real airplanes? Well, as a quick sanity check, let's run the numbers. If you fly a plane at 7 kilometers up, which is about 23,000 feet, the difference between your real physical geometric altitude and this mathematical geopotential altitude is only 0.1%. It is an incredibly tiny difference in the lower atmosphere where the vast majority of flight happens, making this a perfectly brilliant engineering shortcut.
Next up, Part 5, Building the Mathematical Atmosphere.
Armed with our newly simplified hydrostatic equation and our clever geopotential altitude trick, we can now mathematically assemble the sky, layer by layer. And this brings us to the real keystone of the standard atmosphere. In our mathematical model, we don't calculate temperature as we go up. We actually define it first. Based on decades and decades of weather balloon data, we just establish exactly what the baseline temperature is at every altitude. Once the temperature profile is totally locked in, we use our laws of physics, the hydrostatic equation and the ideal gas law, to calculate all the resulting pressures and densities.
Notice how the temperature behaves differently as you climb. At certain altitudes, you hit what we call isothermal regions. In these layers, the temperature stays completely constant as you go higher. Because the temperature isn't changing, the math becomes beautifully elegant, and the air pressure and density simply drop off exponentially as you climb through that specific layer.
But then you have transition zones. These are gradient layers, where the temperature drops steadily as you climb, a slope known as the lapse rate. For example, from sea level up to about 11 kilometers, it just gets colder and colder the higher you go. Because the temperature is actively dropping, we have to use a slightly different formula in these zones to track how the pressure drops, taking that constant cooling into account.
So how do we actually build those giant, intimidating tables of numbers you see in the back of aerospace textbooks? We start right at the bottom, at standard sea level. We define an exact baseline pressure, density, and temperature, like exactly 288.16 Kelvin. Using our formulas, we calculate our way up that first gradient layer until we hit 11 kilometers. Then we take the exact pressure and density at that 11-kilometer mark, and we use those exact numbers as the brand new baseline to start calculating the next layer, the isothermal layer. We literally just leapfrog our way up into space, calculating the top of one layer to use as the base for the next, filling out the massive aerospace tables layer by mathematical layer.
Finally, Part 6, the model's limits.
Before we wrap up this explainer, we really have to look at a common mistake, forgetting the difference between the model and reality. It is so easy to look at a pristine table of numbers and assume that's exactly what the sky is doing today. But let's contrast them. The standard atmosphere is a flawless, frozen mathematical fiction. It assumes gravity never changes, it uses a fake altitude. Its entire purpose is simply to allow aerospace engineers in different countries and even different decades to compare plane designs on an even playing field. The real sky, however, varies constantly with gravity, uses physical geometric altitude, and governs the chaotic daily weather. The model is just an engineering tool, folks. It's not a crystal ball for what the air is actually doing outside your window.
Which leaves us with this final crazy thought experiment. If you magically levitated out of your chair right now
to exactly 3 kilometers above sea level, would you feel the exact standard pressure and density listed in the textbook? The answer is almost certainly no. The actual air would be totally different based on the sun, the season, and whatever local storm system is rolling through. And that highlights the truly fascinating, brilliant reality of aerospace engineering. Engineers must design planes to survive the intensely chaotic, ever-changing real sky using nothing but a perfectly organized, mathematically fake one. It really is a testament to the sheer power of first principles physics. Thanks for joining this explainer, and keep looking up.